My name is Mohit Singh and I'm a static equipment design engineer in Technip FMC. We design heat exchangers and pressure vessels. So I took my project on design analysis of integral voltage flange with a gasket analysis, leakage analysis. So this is a common equipment that we design and analyze daily, day-to-day basis, and we have trouble a lot of times. So that is why I have taken this as a project. So the objective of my project is to design and analyze integral flange upon the stresses in hub and flanges, then gasket leakage analysis and gasket contact pressure analysis, and finally the bolting stress analysis. Moving on, firstly, I would like to have a brief introduction about the flanges. The flange is designed here on the basis of ASME Section 8 Division 1 Appendix 2 guidelines, and the analysis is done using Ansys Workbench static structural module. So generally, flanges are of three types: the integral flanges, loose flanges, and optional flanges. So here in the top right of my presentation, pardon me for my background noise. So in the top right of my presentation, there is an integral flange. In the integral flanges, the pipe, which is called neck, and the flange itself are one body, and they are integral. So they are either welded or they are threaded sometimes. In loose flanges, what happens that the flange and the hub portion are not integral, and generally they are having a temporary kind of joint like a socket weld or threaded portion. Pardon me, in integral flanges there is no threads. So and the third category is optional flanges. In optional flanges, the design is done based on the integral flanges only, but yet the construction may be loose. So the design of flanges involves selection of gasket material, which is very important, then the type of flange facing, the bolting, the hub proportions, flange width, and flange thickness. And all this is done based on the guidelines of ASME in our pressure vessel industry. So the design conditions in here, which I have used for my design analysis, is that the inside diameter, the points in green over here are the input parameters. So inside diameter of the flange is 1175 mm. The flange thickness is around 72 mm. The design pressure is 3.5 bar, and the design temperature is around 150 degrees Celsius. So I would like to have your small attention over the right bottom of the presentation. In the flange, we have different forces. The first force is the bolt load, which is also called bolt pretension, which is required so that the gasket is seated properly and remains in the compressed condition during the operation of the vessel or flange. The second load is the blowout pressure. The blowout pressure is basically the internal pressure which is applied onto the gasket and tries to blow it out of the flange. And if the gasket is not having enough compression load, so the gasket may blow out, and there might be a leakage of the fluid which is flowing through the flange. The third force is a hydrostatic end force, which is basically the force reaction of the internal pressure onto the thickness of the flange, right? So also these are the allowable in this is the image, the allowable stresses which I have shown here. The like for bolt stress, the allowable stress is 130 megapascal, the 103 megapascal at atmosphere design condition, and at atmospheric condition it's 130 megapascals. And the Young's modulus used here is 186 gigapascal for the flange, and 195 gigapascal at atmospheric, and 186 at design conditions. So moving on, one thing more, the width of the gasket I have used here is around 16 mm. So the design load calculation is an important part which is done analytically. I would just like to have your brief attention over here. The flange is designed for two conditions. One is gasket seating and the second is operation conditions. So basically during operation conditions, the hydrostatic end force of the design pressure tends to separate the flanges. To maintain the gasket or joint contact surface under compression to assure a leakage proof tight joint at the design temperature, there is a minimum load required, which is applied through the bolting. So the gasket material and the effective gasket or contact area is to be kept under compression for this. So the equation used for calculating the bolt load in the operating condition is H plus HP, where H is the hydrostatic end force, that is basically nothing but pi by 4 into diameter square at the gasket into design pressure plus the compression force required for the gasket. So the WM1 is basically the sum of both the forces. Now the second condition is gasket seating. The gasket seating is done with, during non-operation condition, where we require the force that is necessary to start the gasket or joint contact surface properly by applying the minimum initial load under atmospheric conditions. This is nothing but pi into width of the gasket into diameter of the gasket into the yield stress of the gasket, right? Out now, both WM1, the bolt load WM1 and WM2 both are calculated, and out of that bolt is selected based on the higher magnitude, which is WM1 or WM2. Generally the WM1 load, which is during operating conditions, is higher. Now I would just like to show you my calculation briefly, where I have calculated the design load pretension for the bolt, which comes out to be 24,892 newtons. So here the nominal diameter of the bolt I have taken as 22 mm, M22 size. So what happens, the minimum bolt load WM1, which I was telling in the PPT, here comes out to be 409,000 newtons. So over here we cannot have a single bolt to allow that much force. So what I have done, I have taken around 36 bolts. Number of bolts here you can see 36. So per bolt I need a total force of 11,000 newtons. Now I have, having a safety margin, I have taken M22 bolt. So the required bolt area I needed was around 4,000 mm square. So per bolt I needed 110 mm square of bolt area. So I have taken M22 bolt size, which is giving me around 272 root area, which is roughly 2.5 times. That is a safety margin of 2.5. Now the flange design bolt load, which comes out to be the greater of the WM1 and WM2. I would also like to tell you that WM2 is coming here 0 because I am using a self-energizing gasket in which the Y is 0. So I don't need this WM2 here because my gasket is self-energizing. So again, coming over here, my flange design bolt load comes to be 896,000 newtons, and divided by 36 bolt, for each bolt I need a pretension of 24,000 newton. This is the same amount load which I will be applying in my FE analysis. Now moving to the geometry, this is a sketch of the geometry I have designed. So you can see all the geometry is in one sketch only because it's an integral flange. That is why. Now this is the bolting on the right side. You can see that M22 size bolting is used. The gasket is over here. This is the hub portion and this is the flange pipe portion. The gasket of width of the gasket is around 15 mm and the thickness of the gasket is 3.5 mm. The material properties for the flange portion and hub portion is stainless steel with a 186 gigapascal of elastic modulus at design temperature. And for the gasket, I have used stainless steel non-linear material. I would like to tell you that the whole analysis is done for linear elastic analysis, but the material over here only for the gasket is used non-linear. This is the mesh. I have used due to design constraints, due to the computer constraints. I have used 5 mm element size. I could not go finer than this, and that's why I have not done any mesh convergence study. But yet I saw that the design, the stresses I got were very much close to my analytical results. So I have not done a mesh convergence study over here. So the contacts I defined, you can see the first contact is nut face to the flange face. The nut face to the flange face, I have taken the frictional contact with a friction coefficient of 0.6. The rest of the settings I have taken program control, and formulation I have used as augmenting Lagrange. Then bolt to bolt hole contact I have taken as rough. And for the gasket to hub, I have taken frictional with a frictional coefficient of 0.2. This friction coefficient I have taken for steel to steel, stainless steel to steel gasket coefficient. Moving on, these are my design boundary conditions. So I have taken the lower flange pipe as fixed support. I have applied 3.5 bar pressure, which I can you can see over here. 3.5 bar or 0.35 megapascal pressure on the inside surface. Then I have taken the frictionless support over here. If I go to my workbench module, so you can see I have taken here the fixed surface, the pressure I have applied over inside of the flange. This is 0.35 megapascal. I have taken two time steps. So the frictionless support, this is an important part that I have applied onto both the sides. Why I have done this? So that because I cannot, I have taken a 10-degree sector. I have not taken the whole geometry. So, but I don't want the flange to move in the circumferential directions like this, neither this direction, neither or this direction. That's why I have applied frictionless supports on both the flange faces. Then I have applied a bolt pretension. Bolt pretension I have applied in the first load step as 24,892, and further I have logged this pretension. So I hope these are clear. And also, yeah, one thing more, I have applied a compensating pressure to keep the body in equilibrium. The compensating pressure is done through the calculation simply, which is applied onto the thickness of the flange pipe, and it comes out to 12.76 megapascals. So I have applied this to keep the model in equilibrium. Now moving on to the results. Firstly, the von Mises stress, which comes out to be 218 megapascals, and it is quite high, and the bolt only, but it's not a thing to worry because we are not, we don't compare the yield stress directly, the von Mises stress to the yield stress over here, because it's a pressure containing part. So, and deformation is 0.28 mm. Now, the first thing, result analysis I have done for the bolt. So I checked through the linearizing the stress through the cross section of the bolt. So over here in the right, you can see the membrane stress comes out to be 63 megapascals. So that's why I was saying that the bolt will not fail, because the bolt analytically also, if we see the bolt load per area divided by the area of the bolt comes out to be 67 megapascals, while the allowable bolt stress is 103 megapascals. So it is clearly validated, and also the 63 megapascals is quite clear, nearer to the analytical result of 67 megapascals, which I calculated. Now moving on, the longitudinal hubs, the stresses which I need to compare. There are three important stresses which I need to compare. Firstly, I'll show you the analytical calculation. So basically, these are flange moment arms, which will finally create the stresses. There are so many factors which all imported from the ASME guidelines. So skipping them, I would like to go to the stress summary. So these are three important stresses which you can see: the longitudinal hub stress, the radial flange stress, and the tangential hub stress. All three I have taken to check the and validate the FEA results. So firstly, longitudinal hub stress, SHO. So you can see the longitudinal hub stress over here. So it comes out to with 93.9. I've done three iterations. It's around 100 megapascals. So it is quite near to my analytical design calculation, 104 megapascals, and it is less than the allowable 131 megapascals. So it is passed on this basis. On the second one is the radial hub stress. So radial hub stress is nothing but here. So for the radial hub stress, as you can see over here in the right side, I need to linearize it, linearize the stress to obtain the right magnitude. So when I linearized, it comes out to be 3.77 megapascals, and analytically also it comes out to 3.11. So it's quite close, and it's less than the design allowable limit, which is 87 megapascals. So it is validated over here. The third and final stress I calculated is tangential flange stress. So this stress also needs to be linearized. That's why I've linearized it. And but yet the magnitude over here and here in the linearized also is coming around 30 and 27. So it's also very much close, 30 megapascals, which is less than the design limit, 87 megapascals. So all the parameters it's passing. Rest of the parameters are not very much stringent. So I have taken only these three parameters to validate my FEA model. Now moving on, this was the hub stress analysis. Now gasket contact. I also need to validate if my gasket in the operating conditions is close enough and having a close contact with the flange so that there is no leakage. So as you can see, the gasket contacts are quite sticking and very much close. So and the bolts are also very much close to the bolt hole. So there is no way of any leakage. Also, you could see that the whole gasket is not in the close contact status, but only a portion of it. This is because the gasket is not the whole width of the gasket is not used. In the next slide, I will show you why. So firstly, let's see the gasket contact pressures. As you can see, the gasket contact pressures are nearly 0 to up to 3/4 of the width. And only at the boundary, near boundary, it's having a positive magnitude around 38 megapascals. So why is it so? Because ASME guidelines just tell you that the effective width is only n/4. N is the total width, but only 1/4 of the width is used to leak the gasket, because due to the bolt loading, there is a momentum created which releases the pressure, contact pressure from here, and only the periphery of the gasket is able to have a leakage proof joint compression load. So that is why we are having only here a positive magnitude of contact pressure, but still it is high, and throughout the periphery it's positive. So we are having a leakage proof joint. The third, bolt pretension also need to be validated. I need to see that my bolt is enough loaded even in the operating conditions, because during the operating conditions, the hydrostatic force of the internal pressure will try to depart the two flanges. So my bolt load should be enough to maintain the contact pressure on the gasket. So as we you know that we applied 24,000 of newtons of bolt pretension in step 1, which was only there was no operating pressure, only atmospheric conditions. But on the step 2, the operating pressure was applied. So it is expected that the bolt pretension will decrease. So as we can see from here, the tabular data, in the load step 2, the bolt pretension is decreased to 22,000 newtons, which is around 2,200 newtons of the bolt pretension is decreased because of the reaction of the hydrostatic end force. But still, in the calculation we saw minimum required bolt load, WM1, per unit bolt was 11,000 Newton, and my bolt pretension is still in a more than 11,000 Newton, which is 22,000 Newton. So my bolts are well in having a compression load onto the gasket to prevent any leakage. So concluding, the stresses in the components are within permissible limits, and gasket contact pressure is more than the design pressure during operation, and thus the leakage is also prevented. So this was the analysis of the voltage integral flange.